Let me try to give a feel for the numbers involved. Imagine some future quantum computer that's performing Grover's algorithm. Say it has a quantum processor capable of performing 100 million calls of criterion f per second. And suppose it's engaged in a particularly arduous search through a space of 10 to the 30 possible solutions, looking for them with f of t equals -1. How long will that take? Well, it'll require about 10 to the 15 calls of f, which at 100 million calls per second will take about 10 to the 7 seconds, or about 4 months. A classical computer with the same processor speed would require about 5 times 10 to the 29 calls of f, which would take it 5 times 10 to the 21 seconds, or very nearly the age of the universe. That's the size of the practical benefit of the quantum search algorithm over the classical. But the theoretical implication is even more mind-boggling, because we know how Grover's algorithm works. It isn't just doing 10 to the 15 evaluations of f in parallel, which you could mimic classically by, say, making all the computers on Earth work on nothing but this problem. The quantum processor is doing 10 to the 30 possible computations of f in parallel every time it's invoked. If all the silicon in the whole of our planet were made into microchips of 1 cubic millimeter each, and they were all set performing different computations, there'd still be fewer distinct computations going on in that giant parallel computer than there would be in a single quantum processor performing Grover's algorithm. That's a measure of the complexity of structure and process that exists in ordinary matter just beyond our perception, because quantum processes are, of course, going on all the time, everywhere. In a quantum computer, some small part of that complexity is put to good use.